There we go. Should be running. So there will be office hours available to you guys sometime in the future, but I don't know what that will look like and when. That will be entirely up to Dr. Wright to set up. So at this point, we're not expecting me to be the instructor for the semester, just for the interim. Accordingly, that means that policies, there will be 3 exams during the course of this semester. There won't be makeup exams, quizzes or homeworks, anything like that. Graded material is sometimes going to include worksheets and things of that nature that will be brought into class. A lot of times there's specifically some exercises regarding crystallographic planes and determination of the planar alignment metrics, some of those sorts of things that you just need to know something about. Okay, so homework assignments, those are going to be in Halo. So here again, not Canvas, but in Halo. So you're not looking for something that doesn't exist. They will be posted in Halo. You guys are all going to be running through Wiley Plus, but I still need to get that set up because I have not had the time or bandwidth to do so. I need to see if I can get it cloned over from one of the other previous sections, and we'll see how all of that goes. That usually ends in many steps, so it'll take maybe a couple days to get that running. The materials will be due typically if there's something that needs to be turned in, it'll be at the beginning of class. And Dr. Wright has a very simple, plain, no late assignments. So that applies whether it's 2 years late or 2 minutes late. It's all the same thing in her book. So just understand that that's an expectation up front. Again, this first about week or so while we're trying to unscramble the mess, we'll be paying attention to due dates so that you guys aren't being asked to do something within the next 5 minutes or get no points. So we're not trying to be intentionally unfair, but we have to maintain a equal weights and measures throughout the semester for everyone. So there are a couple of things that allow for uploads. Like there's a number of ways to turn stuff in, but the general suggestion here is when uploading to Halo, any of the assignments, make sure that you're uploading them as Word docs with clear images and things of that nature. Make sure it includes all the pages and that you didn't, like, you're not saving everything with untitled.doc. There's another thing that Dr. Wright prefers in terms of the mechanics of turning in assignments. You'll need to pay attention to how some of this goes. She prefers to have a specific sequence, and I'll have to look and see if I can find it. It's something like the class section number, so it needs to include your name and your class section number so that she can keep track of it more easily, because she will download things and she has kind of a whole process for that. So a lot of the homework itself is all going to be through Wiley Plus. So this applies mostly to a couple of the exercises later in the semester. So I'm sure she'll reinforce those. But those are things that you need to be paying attention to. So make sure stuff's clearly labeled and you're not just uploading things with file names of untitled document. That's how you end up losing what thing you were working on, and just generally a bad policy to leave it as untitled document. So grades will be kept in Halo, which is, of course, the greatest of all software. So this may or may not apply for the semester. I left it in because there are some instances where Dr. Wright will allow one sick homework or something like that. I don't know if that's still part of her policy. That used to be. So don't expect that that will be the case. That's on a discretionary basis and usually is used for the like grandparent died sort of life event. So don't expect that, oh, I was out having too many taco sandwiches with my friends last night and I forgot the homework. It's probably not going to get you very far. So point scale, we're not going to focus on because all of the point values are different from this section that she taught to today. So don't worry about that. Calculators are allowed. These are things that you're going to need for certain problems, making sure that they are scientific calculators are important. There may be some additional perspectives there, but for sure you're not on your phone in tests. That should be pretty clear. You're usually not on computers during tests, etc. There are often times where you will have slide sets posted by Dr. Wright. We may or may not get to that because this couple weeks proves to be often pretty chaotic. So you're more than welcome to take notes. In this case, I'm at least recording things. In general, the recording from you guys of the lectures is prohibited because there's a long series of reasons why. So we went through the syllabus. Now we'll get into kind of the core, which is what is material science and why should you care? Why is it important? Why are you in this class? If you're flying in an airplane and something like this happens, turns out that's bad. If you're driving across a bridge and something like this happens, turns out that's bad. So we want to not have these kinds of things happening. Probably a few of you have experienced this, right? F in chat for how many screens you've lost. I'm sure there's been a few. And then similarly, even in biomaterials, fractures, right? Really bad things happen. So we've been through a series of ages. Stone Age, the very first kinds of tools and simple materials, pick up a rock and turn it into a hammer or death bludgeon. That was one of the first recorded uses of stones as tools. So Bronze Age, start figuring out how to take stones and take the metal out of stones and make tools and implements. Then the Iron Age, make harder, sharper tools and actually start making tools that can help to work on the rock. And then now we're into what arguably will be the silicon or glass age. There's some argumentation on how this will be remembered, but concepts like flexible circuitry, things like that. You guys now who have made the poor life choice of flexible glass screen phones will learn some things about material science and why that's just not actually a good idea. So hopefully Dr. Wright will get to incorporate some of that into the latter stages. So there's a few examples, especially things like in cancer therapies and all sorts of things. There's all of these different kinds of polymers that we're using, including specifically designed polymers to mimic parts of biological components, virus-like particles for training immune systems, or intentionally lab-designed infections like COVID. Right? So there's lots of things that we're using these unusual materials for, and why we need to know why they're going to do what they're going to do in the case of polymers and things like that. So a hip implant is a good example of something that has stringent materials requirements. As people age, for instance, you have something that has a rather surprisingly large load, like a hip, and you think about the fact that if you jump off of some object that is proportional to your height, 5-6 feet, something like that, that actually becomes quite a bit of load that typically is landing primarily on one side, one hip. So there is a lot of load that is placed on the hip, and specifically the head of the femur and the socket that it sits in. So a normal, healthy one on the left is depicted, one that is what looks to be slightly abducted is maybe, yeah, it looks slightly abducted on the right side. So a lot of that material has degenerated, and the head of the femur has been compressed significantly. So a lot of degeneration there. In order to replace that material, there's a bunch of different kinds of considerations. And this is not something that you guys need to memorize. This is just something to be aware of, because of the way that this works or the way that this behaves. With many, many, many repeated cycles of movement and motion, the mechanical strength has to be very high. It has to not bend and flex. The surface also has to have a high degree of lubricity, meaning it is easy to have it slide past another surface with very low friction coefficient. So there's the acetabular cup that the head sits in, and that's where you have to have a very low friction, very highly lubrous surface. And additionally, that material is also going to have to be biocompatible, meaning it can't be something like mild steel that's going to rust and create all sorts of irritation and shed dust. I mean, imagine the idea of actually being a tin man and trying to get up out of your seat, and you're literally rusted into place, and you have to break that rust in order to move. Walking down the hall with your hip going, ee-ah, 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 it's not going to work, right? So you have to think through all of the levels and layers of requirements of the material, and that really greatly limits the kind of material that you can use. So this is part of what we have to think about when we're looking at these things. So what do we do when we go to replace one of these? We take the pelvis, we replace what is called the acetabulum, the acetabular region, with a cup. There is a fixation agent, meaning it's a bioadhesive. It's a glue that sticks to cells. That cup is designed to be highly lubrous. The ball itself has to be a very fine mirror polish and have no surface imperfections. There has to be a stem that gets driven literally by hammer down into the femur itself, and hope they don't split the femur in the process. Those surgeries are super fun to watch because they have like 12 people and they get in there with a sledgehammer, and it's awesome. There's no wonder why people need to recover after hip surgery. Super primal, it's wild. But that has to be much smaller than the original bone and much stronger at the same time. So let's see in chat, what kind of material do you guys think that that actual ball and femoral stem have to be made of? Give me some examples of what you think would be a good material based on what we've described. Let's see what your answers look like. A lot of guesses for titanium. Some graphene, wood. I mean, wood is sort of biocompatible, so that's a reasonable guess. Wood turns out to be not strong enough. You would think something like carbon fiber. Carbon fiber, while stiff enough, cannot wear because it doesn't have a high enough surface hardness to be able to meet the criteria for the ball. So that's a good guess. Delrin is probably an okay material for the acetabular cup, at least in terms of being durable, being able to be very smooth and highly lubrous. So that's good. It's a good guess. Titanium, a lot of guesses for titanium. And we do a lot of implants in titanium, but there's another common material, and I haven't seen it come up. Graphene is too difficult to structure in something like this because graphene is in sheets. So that tends to have a low bond strength between the sheets of carbon. So it's a good guess, but the ball itself needs to never, ever, ever be shedding material. So steel, ceramics are a really good guess. Ceramics are extremely hard, and that's pretty close. Titanium, it turns out, is too soft because if you actually were to make one of these purely out of titanium, for the most part, they would not be able to be strong enough. They would have to physically be a larger size in order to be strong enough because titanium is actually softer and easier to bend than stainless steel. So if you look at what people did in terms of durability testing of the iPhone 15s, the titanium frames are less durable. So people are able to just with their bare hands bend them and snap the glass, snap the back glass. They can literally bend it with their bare hands and shatter the glass. So if you happen to sit on it or something, you turn your phone into the shape of a cereal bowl and now it doesn't work so good, right? Gold is highly biocompatible, so that's good. But gold is extremely soft. It's one of the softest of the metals, and that's why it makes such a great foil. You'll learn why in some of the coming lectures as far as the molecular interactions. Steel, it can't be mild steel. Stainless steel is another one that people often think of as, well, we put a lot of stainless steel stuff in the body, and that's also true, but even the stainless steel is too fragile, so it's too easy to bend, and it has to be much, much stronger than stainless can be at this end. Sometimes part of the implant could be titanium, and then they have a different material for the ball. Sometimes that happens, but if you're going to make it all out of one material, we actually end up having to use a cobalt steel, which is a very extreme sort of tool steel in order to make these. So it's still a stainless sort of material, but it's much, much, much harder, much stiffer specifically, much harder to bend, and it's very, very, very strong material. So good guesses, but that at least tells me you guys are thinking, which is a good start. So we need a few things that we have to overcome. We have to have the cup and liner, and then we have to avoid the debris in the cups, all the things that we've just covered. It's almost like I've taught this kind of material before. So the types of the material, they have to be strong, somewhat ductile and not brittle, so that you don't jump off of that 5 or 6 foot height and then have your hip implant shatter under you and you just become a lump of flesh on the floor. That would not be good. Needs to be opaque, and it needs to be highly polished to be able to be reflective. And so those are some of the kinds of characteristics, but these are things that are characteristic of metals. So they're strong, they're ductile, they are highly thermally and electrically conductive, they are opaque, and they are reflective typically. Polymers share electrons a little bit differently. So they have covalent bonding. They tend to be soft, ductile, they're low strength, and they are low density, meaning they are lighter weight typically than metals. They are better insulators against thermal and electrical. They also have optical transparency, which is great. Some of them, however, are only translucent, so things like the last Coke or soda or even plastic water bottle that you got or anything of that nature, those sorts of things are characteristic of polymers. The ceramics, however, there's a couple different kinds. They are compounds of metallic and non-metallic elements, often oxides, nitrides, sulfides. So it's not uncommon for us to have ceramic coated metal tools, especially things like cutting tools. Nitrided tools or nitrided metals sometimes can tend to have a gold-like finish. For instance, they tend to be much harder. They wear better over the course of time. They maintain lubricity, and so they're a premium metal finish, but they're premium metal finish for a reason. But the downside to ceramics is because they tend to be so hard, they also tend to be very brittle, and that's part of the cost trade. So in all of engineering, there's always cost trade. Something like gold is extremely biocompatible. The body will never react to gold in the body because gold doesn't oxidize. It doesn't change electrochemistry. It doesn't change. It's always gold all the time. And that's why some of the people would use gold early on as fillings. Then they went to these more toxic amalgams, and that's another lecture for another class. But these ceramics are non-conducting. These are very, very important materials, especially for control of electrical power lines and things like that. All of those ceramic insulators and things that you have, just like on the spark plugs. Those are absolute marvel of materials, the modern spark plug is. But it's a very inexpensive thing that you never think about because you just haven't had the exposure to why this is such an amazing material. So the selection process looks something like we start with an application and then we look at what are the required properties. So just like the hip example, we know what the application is. Then we have to figure out what kind of mechanical, electrical, thermal, magnetic, optical, and deteriorative properties those have. So in order to make these work, we then go from the properties to identifying candidate materials so that have the right sort of structure and composition. Then we need to identify what kind of processing is going to be happening, right? So the way that we process the material also changes the structure and the shape. So is it going to be a cast material? Is it going to be sintered? Is it going to be vapor deposition? Is it going to be some sort of doping like we do for a lot of the glass materials that we're using now? Is it going to be hot or cold forming? Is it going to be a joining, some kind of joining method? Is it going to be something like lap joint with bolts? Is it going to be some kind of butt joint with a weld? That creates additional thermal changes in the material. Is it going to be annealed afterwards in order to sort of recrystallize the material and change its properties? All of that comes down to what are the actual atoms doing? And that's what this is. So I want to pause for just a second and see if there's any questions on this so far. Anybody like super unclear about the hip example, or anybody like super lost at the moment? Or is everybody pretty okay? No major questions coming up? Okay. Good. This should all be pretty much straightforward. So I just want to make sure that we're sensitive to questions coming up. All right. So structure, characterization, processing, performance, and properties. Characterization of the materials is understanding all of these things all at the same time. What is the actual structure of the material? What are the properties that it has? How is it going to perform? And what was the processing used? All of that goes into characterizing the material. You need to know everything about it so that you can predict what it's going to do under certain conditions. So the goals of this course are to be able to get you to understand how to select the right material for the job. Again, it's not as simple as, do I make it out of aluminum or do I make it out of steel? It's just not that simple. And more and more vehicles, even in the automotive industry and all sorts of things, are starting to use more exotic and more expensive materials. So it's not just that they're adding in more technology, and that's making the cars more expensive. They're using more exotic materials. They're using more rigid steel for the frames. They're making things bigger and heavier, but they also need to make things bigger and heavier without making them more dangerous in crashes, meaning they have to design stronger things with much weaker zones in a very strong material, for instance. And these are the kinds of things that you have to do in order to be able to design new stuff. A good example is most of you are familiar, because you're familiar with any kind of video or social media platform. Most of you have seen something about the Cybertruck. The Cybertruck uses a new classification of steel for its exoskeleton that they had to create in order to get the properties that they wanted to have the right balance of strength and resistance to oxidation. So it's a cool truck because of the engineering that went into it, not necessarily because of anybody that was associated in its development. So these are things that we need to understand, is just because there's stainless steels out there, they didn't take an off-the-shelf stainless steel because that wouldn't do the things that they wanted. They wanted something that was going to be very strong and very dent resistant, but stainless steels tend to be softer when you introduce the chromium in order to resist the corrosion. So there's a cost trade. They decided to engineer a new material in order to sort of not bypass the cost trade, but to get the things that they wanted in the end design. So we need to recognize how the design of a new material works, and I'm hoping that we can use some of those as examples. So I want to see if I have, I want to see, no, it does not work so well for towing, because it turns out it's extremely hard to get a sufficient energy density into electronic batteries. That's the big kicker with all electric vehicles. So when people come in and they start talking about how there's all of this mess with, they're going to do electric semis and things, in order to get sufficient energy density at this point in time with current level of battery technology, an electric semi is a disastrous, terrible idea. There are fundamentals of physics that are resisting your advances, and that's all there is to it. So that's kind of an introduction to the first chapter. We're going to get a little bit into some of chapter 2. Yeah, the steel that they use is pretty interesting, and there's there are some folks that are still converting those to electric, and it can be done, but what you compromise there is you now end up with long recharge times compared to a gas fill up, and the fundamental physics you're fighting is the energy density of the batteries is about 1/10 that of a good liquid fuel. So you need 10 times the mass of batteries to get the same level of energy content that's in a certain volume of a liquid fuel. That's the problem, or the certain mass rather. So it's a mass to mass comparison. When batteries can get closer and close that threshold, then we can do that. The cost trade, again, because everything is a cost trade, the more energy you pack into that space, conversely, the more dangerous it becomes, and it becomes unsafe on impact, for instance. So it's also very, very, very dangerous. That has a couple things going on. So the people that are smart are the ones that, like you're mentioning, Morgan, that are going with basically a diesel electric setup, which is what trains have been doing for almost 100 years now. So this super duper efficient transportation system was solved 100 years ago by the train industry. Why it's taken everybody else so long to figure out, gee, maybe we should do diesel electric. Um, Reasons. Americans like their V8 power. It's just the way it is. Okay. So we like internal combustion. Um, Diesel electric like that, where you're primarily electrified, but you have a diesel generator, lots of torque. You can generate a lot of power without a lot of fuel. That's the right way to go. So, this is a fundamental, again, materials trade-off. But as they get to have higher and higher densities for these things, there's a lot of challenges that come up. So, all right, I'm going to set up one more here. We're going to start just touching chapter 2. This way you guys will have a little bit more of the background material because we need to get into the meat and potatoes this week as best we're able. That way you can get a little bit of a sense of what's going on. So again, this is wrong course number on these, but at least right color border because all things should be purple with a very specific RGB number. Okay. Having said that, the way that we understand atomic bonding and interaction between these atoms is critical. There's a lot that goes into this, and the ion-ion interactions are very important. What you will get is as this this is the internal energy as a function of radius or distance from the internal radius as a function of distance. Let me grab this real quick. Yep, more chaos ensues. Okay, so as the distance, so this x-axis is representing distance. It's not important to remember all of these equations at the moment, just to understand this proportional relationship with as the internal energy as a function of distance, radius from the center point between the two atoms. As that energy, as that distance increases, the actual energy between them decreases down to a low point, and this is where the binding energy occurs, the difference between the zero state and that energy well. That distance is the binding energy, referred to as U naught. The idea there being this is the energy that you have to overcome, that amount of barrier. That is the energy you have to be able to overcome in order to break the bonds apart. And there's attractive forces and things that as you physically separate them farther and farther, that energy becomes less and less and less and less. So as you stretch them harder and harder, typically by increasing the temperature, this is why we do reactions at higher temperatures. So again, stuff that you guys have seen in a lot of other varieties. There's a lot that's going on there, a lot of binding energy reduction that happens as those bonds are stretched and stretched and stretched and stretched. It's easier to break them. That energy becomes less and less, and it's easier to have a resultant energy that allows for breaking the bond. So we need to just understand a couple of things about the way that these work. And so this is kind of both chapters 1 and 2, and they really kind of run together. But I'm going to try and get you guys through as much as we can of 1 and 2 so that you have kind of the fundamentals, and then you can really focus on the way that these apply to the situation. So understanding the classification of the materials, so metal, ceramic, polymers, composites, the atomic structures, understanding the construct of the atoms, some of those things, being able to understand the periodic table of elements. Go ahead and give me a +1 in chat if you guys have already been through 2 semesters of Gen Chem. So you've done the Gen Chem 1 and 2. Let me see where everybody's at with that. Because I expect about everybody, but if you haven't and you've not had chemistry and you're somehow in this class because prerequisites aren't a thing, that can create lots of unnecessary confusion. Okay, so we broadly understand that atoms are things. They're really small. It's very hard to see them. Okay, good. And I know we don't have lots more time, so we'll try and be efficient with this. I just want to try and get you guys as best set up as possible. So the periodic table of elements we need to be at least familiar with. We're going to talk about 3 binding mechanisms: metallic, covalent, and ionic. These are really critical because of their involvement in the macro scale behavior of materials. These are going to be part of discussing what these do in terms of affecting strength, ductility, electrical conductivity, and other properties that become high or low as a result of what type of bonding they have. So ceramics, for instance, are very high in the ionic bonding, meaning it's very hard for them to transfer electrons across their surfaces because they've already got a high electronic or a high electrostatic difference between these two. And this gives us something to work with. So there's a few things that we can do here. So explaining the secondary and tertiary van der Waals components will kind of help. So we're also going to define what is exactly the binding energy and how does that look. And then we're going to be citing the mechanism for the elastic deformation. And we're going to understand some more things about that. We're going to understand single crystal and polycrystalline materials. What are the difference between those? For instance, those have a big effect on solar panels and what that looks like. And then understanding what a polymorphism is and how that functions is another big factor. And what the lattice behavior is, understanding simple cubic, body-centered cubic, face-centered cubic, and then hexagonal close packing lattices and what some of those things are, how those behave, how to understand the lattice parameters, what those things mean. The lattice parameter A, what that does in reference to the radii for the face-centered and body-centered cubic crystal structures, determining packing factors, all of those sorts of things. So there's a lot of depth that we're going to get into in this, as well as distinguishing between anisotropic and isotropic materials, sort of what all of that looks like. There's a lot. So we're going to look at, we have, I think, just enough time to kind of look into what's actually promoting bonding, what those types are, and what are things that are going to interfere with bonding so that we understand how some of these things behave. So things that you guys have seen, an atom has electrons that have a mass of about 9 times 10 to the minus 31 kilograms. Protons and neutrons are on the order of about 1.6 times 10 to the minus 27 kilograms. So the mass of the electrons is very, very, very small, almost infinitesimally small. The atomic number, so as just a quick refresher, that's protons in the nucleus. Also the number of electrons for a neutral state species in terms of the electrochemistry. They all have a number of atomic mass units, and these are things that you guys are familiar with, so we're not going to spend tons of time. But as an example, the atomic weight of 6.02 times 10 to the 23rd molecules per atom, molecules or atoms per mole. Same for atomic mass units. 1 atomic mass unit per atom is the same as 1 gram per mole. So using Avogadro's number, we understand that the carbon has 12.011 grams per mole, and hydrogen has 1.008 grams per mole, which will help things significantly. So that will help kind of get you guys into the right state and give you guys a best let's see. Yeah, give you guys a best practice. Let's take a look there. Yeah, we'll do some kind of coverage of all of this and how it works. The following properties we're going to get into a little bit, probably for Friday, because we'll get a little bit farther into this. But where we're headed is understanding the chemical, electrical, thermal, and optical properties that are determined by the electronic structure of these materials. So there's a lot to go over in terms of those. There's a lot that we're going to get into in how these actually operate. So, all right. That's a lot of information. What I'm going to do is jump back in because I know everybody's going to have to start rushing away to next classes. So we're going to stop the recording here, but I'm going to check in any questions at this point.